All right, we're on our benchmark review. We're looking at examples. So we're looking at these transformations. So this picture is a reflection. It's a mirror image over a line. This next one is a dilation because it has a change in size. This next one is a translation because all it does is move from one place to another. Here we have a rotation as our shape rotates around a point. And then this last one is called a glide reflection because it has both a move and a reflection. So it can either move by translating or by rotating and then reflecting. So you can tell a glide reflection because it's reflected, it's backwards, but it's not going to be directly across a line. All right, let's look at some of these pictures and see what kind of symmetry they have. So this one has reflection symmetry because we can fold it down the middle and it looks the same on both sides. This one has rotation symmetry because as we rotate it around, each little piece looks the same. There's a pattern here of 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that means that it would rotate every 36 degrees because we would go 360 divided by 10. So that's a 36 degree rotation. Superman sadly has no symmetry, even though an S can be symmetric when you turn it upside down if it's drawn right, but not this one. And then this one has both reflection and rotation. We're going to look at this one that has both right here. I counted up the number of repeats in the pattern and there are 9. So that tells me there are going to be 9 lines of symmetry. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 lines of symmetry, but we also have a pattern that repeats on a rotation 9 times. So we can do our angle of rotation by taking 360 degrees and divide by 9. And that gives us 40 degrees for each rotation. Each time it rotates onto itself, it's 40 degrees. All right, what do we call a pattern that is created by repeating and transforming a shape to fill a two-dimensional space? We made these in class. This is called a tessellation. Name an artist that uses geometry in his artwork. The name of the man that we talked about, his name is M.C. Escher. Just has lots of geometry and lots of tessellations in his artwork. Like we looked at some that have tessellating horses or lizards or birds and fish, things like that. Okay, don't mix up a tessellation with a fractal because a fractal repeats itself, but it changes sizes. So different scales means the size changes. So that's kind of the difference between a tessellation and a fractal, is that the size changes, like smaller, 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 or bigger, bigger, bigger. Okay, so that's called a fractal. Fractals can be seen in hurricanes or seashells, and that type of fractal is known as a spiral fractal, where it just spirals in closer and closer or spirals outward further and further away. A fractal that can only be generated by a computer is an algebraic fractal because it takes an equation and creates a complicated image out of the equation. Sierpinski's triangle is what you might call a triforce in Zelda. Sierpinski's triangle is made of triangles, and the triangles keep getting smaller and smaller, so like many triforces put together. Anyway, see how this pattern just can keep repeating smaller and smaller. So that is called a geometric fractal. And then things like river systems or veins in our bodies, where the veins can be bigger and then they branch out into smaller and smaller branches, are called branching fractals. So those are the 4 types of fractals. There's just the 4 types. So a snowflake would probably also be a branching fractal. The little ice crystals branch out. There's also another kind of snowflake called a Koch snowflake that has like a geometric pattern, something like that. So we will be looking at that later, probably in January when we come back. And that one is considered to be a geometric fractal because it's made of just shapes that get smaller and smaller. Okay, what are fractals good for? So in technology, they are used for cell phone antennas. So it allows us to have really small cell phones with really good service, hopefully. And in medicine, they can be used to study things like cancer, because the veins in cancerous cells, the veins running through them, is different than normal veins. Can be used to study veins, just the vascular system. Can be used to study our lungs, because they contain fractals. Branching fractals in our lungs that help us to breathe as much air as we possibly can.